Welcome to the first Jones seminar of the term. Thank you all for coming. We have a great turnout today here in the room, and it looks like we have a good number of participants on Zoom as well. So today we welcome Professor Michael Dickey. Michael is the Camille and Henry Dreyfus Professor and University Faculty Scholar in the Chemical and Biochemical Engineering Department at North Carolina State University. Michael received his BS in Chemical Engineering from Georgia Tech and a PhD from the University of Texas under the guidance of Professor Grant Wilson. And from 2006 to 2008, he was a postdoc fellow in the lab of George Whitesides at Harvard. He completed a sabbatical at Microsoft in 2016, and I have learned that he's about to complete another sabbatical in Switzerland this year. And Michael's research interests include soft matter, such as liquid metals, gels, and polymers for soft and stretchable devices, electronics, energy harvesters, textiles, and soft robotics. He's also a recipient of a large number of awards, including the NSF Career Award, the Curtis McGraw Research Award, and the SPIE Nano Engineering Award. So join me in welcoming Michael.
Okay. Well, thank you very much for the nice introduction. Thank you for having me. I've had a really lovely visit here. It's a beautiful place. And thank you all for coming. I hope it wasn't just for the cookies, but at least you got cookies. So I've got a lot of fun stuff to show you. So I hope that it will go a little bit beyond the cookies. But hoping to share with you some work that we've done at NC State in our group on liquid metals. And everything good? Okay, cool. So as Will alluded to, in our group, we work on a number of different things, united by the importance of these words: interfaces, patterning, and soft materials. And those words are very vague. So if they don't mean much to you, that's kind of on purpose because they encapsulate a lot of different things that we do. But I'm going to give you just a tease of some stuff that I'm not going to talk about. But one of the things we work on is actuating polymer. So in this video, we take a flat sheet of polymer and we shine light on it. Good reaction, thank you. This is interactive, so please, I love to hear the reactions. So what we're doing here is, maybe I'll play it one more time in case you're not paying attention. So what we're doing here is the black ink is literally toner from a printer. So very, very simple. You can do this at home. And when you shine light on it, the black ink gets hot because it absorbs the light and it causes the material to shrink and therefore fold. More recently, we've been working with Nathan Lazarus at Army Research Labs and using a laser under different settings. One setting cuts this printed circuit board, and a different setting causes the printed circuit board to fold. Throughout this process, you'll see that the LED, which is in the middle, continues to operate. So the idea here is you make electronics in 2D, and then using this single piece of equipment, cut the material and also get it to assemble into three-dimensional shapes. So sorry for the tease, but we're not going to talk about that, but I'd be happy to answer questions. But I am going to talk about our work on liquid metals. And the motivation here is shown by this picture. So this is a picture of obviously a human hand in contact with a robotic hand. And what I'm trying to illustrate here is that a lot of the devices that you have, maybe cell phone that you have in your pocket or a laptop, or if you're really sophisticated, maybe a robot, tend to be made out of rigid materials. But of course, our bodies are made out of soft materials. So there's a lot of interest in trying to mimic some of the amazing things that the body can do, or simply just interface these types of devices with humans in a safe and comfortable way. Okay. So how do we do this? Well, one way that people do this is to make things flexible. And I put flexible as easy. It's in quotes because it's easy only conceptually. I know there's some groups here that do this in practice and they know that this is actually difficult, but conceptually you can imagine if you take a piece of wood, which is great for building a house, and you make it thin enough, you have a piece of paper. Same thing if you take a big chunk of aluminum, you can make a bike frame out of it. It's very sturdy and light, but if you make it thin enough, you have aluminum foil. And of course, these things are flexible, but they're neither soft nor stretchable in their particular forms. So what we've tried to do is to use materials that are inherently soft. So this is a plot of the Young's modulus, kind of a measure of how hard materials are. And way over here you have diamond, If you go 1,000,000 times softer, you get down into the world of rubber. If you go 1,000 times softer than that, you get down into the world of biology. And if you go all the way to the left, you see liquid metals. Now, what is the first thing that typically comes to mind when you think of liquid metals? If you're in Will's group, you can't answer this. Mercury or... Oh, you're too smart. Mercury or what? It starts with a T? Oh, you guys are all too young. Some of the older people. It's a movie. Only one person knows the Terminator?
Terminator.
You guys spend too much time studying. Well, if you've lived a deprived life and have not seen the Terminator, let me show you. So, there's a little bit of lag. Okay, there we go. So this is a clip from the Terminator. That's the former governor of California. And he has just blown up the bad guy. And the bad guy is this creepy material that gets destroyed, but then it comes back together. And, well, I like to show this because mostly just for fun. Usually people shout out Terminator, but it didn't work this time. Too much time when you're studying your books. Anyway, so, liquids typically don't do these things. They don't take on human-like shapes, right? They typically take on spherical shapes due to surface tension. We would like to be able to take liquids and make them into shapes like wires and other useful electronics things. So this is kind of trying to motivate that. I actually had the good fortune of talking to the guy that did the special effects for this. His name's Gene Warren Jr., and he won the Academy Award. First foray into computer graphic rendering, and he actually used mercury to do this. So anyway, he passed away a couple years ago, but this was a really monumental movie. So you should check it out. All right, so how do you pick a liquid metal? Usually a couple people shouted out mercury, and that's correct. It's toxic, so we don't want to use that. There's also these elements over here that have low melting points, but they're really nasty. They're explosive, radioactive, etc. So by process of elimination, that leaves gallium. And I'd like to point out something to you, and that is that gallium is right below aluminum on the periodic table. That's to say that they're like brothers or sisters. They have very similar properties. But there's one big difference, and that is gallium has a very low melting point. So this is a picture of gallium. You see its melting point is 30 degrees Celsius. That's about 86 Fahrenheit. So if you held it in your hand, it would melt, turn into a liquid. We don't want to hold it in our hand for all of our experiments. So we add in indium. Actually, we buy these already mixed together, and you get a liquid with a depressed melting point. Now, I'm not going to try to not use jargon, but sometimes you'll hear me say E-gain if I slip up, and that stands for eutectic gallium indium. Eutectic just means the composition with the lowest melting point. So that happens to be about 75% this and the remainder indium. This is, in my opinion, one of the most interesting materials on the periodic table. Well, this is on the periodic table. It's got a water-like viscosity, so think of it like metallic water. It has zero vapor pressure. That's very unusual for a liquid. Most of you, I hope, took a shower this morning, dried off, hung up your towel, and tomorrow it will be dry because water has a vapor pressure. It evaporates. This has zero vapor pressure. It's very unusual. It's got low toxicity. It expands when it freezes. It's got a really large surface tension, which I'll talk about in a second. But for our purposes, the interesting thing is it reacts with air to form an oxide on its surface. So that's actually not surprising because aluminum does the same thing. You may not know this, but aluminum is very reactive. Now, how can that be that it's very reactive, but every one of you probably has this in your kitchen? Well, the reason you can safely have it in your kitchen is because it does react with the air and forms an oxide, and that oxide protects the metal from additional reactions. Without that, it would just get chewed up, and we wouldn't have aluminum in our society. So this is what it looks like. If you do a cross-sectional view, here's this oxide layer, which is only about 3 nanometers thick. So it's only a few molecules thick. And the importance of it, again, is that out here you have, say, air, or in this case, vacuum, and then here's the metal, and it protects it. So it's called passivating. It protects the metal. So this is the most important slide, so take your eyes off your cell phone for a second, in case you're... so this is the metal spread out on the glass slide, and if you dip this Q-tip into this vial, you'll get a little bit of acid on it, and that vapor from that acid dissolves off that oxide layer. So this is kind of the punchline of a lot of things I'm going to show you. In air, it forms this oxide. It's like a waterbed. It forms a skin, but we can dissolve it off using acid. Now, you might remember we added indium to the metal to depress its melting point, but that oxide is gallium oxide. It's the most energetically favorable, and it forms very, very quickly. So you might be thinking, why is this crazy guy making a big deal about an oxide layer? Well, usually, if you want a metal, you want a metal. You don't want an oxide on the surface. Well, what this does is it allows us to shape the metal sort of like the Terminator, in ways that would simply not be possible using other low viscosity liquids. So here, if we suck the liquid back into this nozzle, you see the oxide skin. Remember, it's only about 3 nanometers thick. You see it wrinkle. And this layer forms so fast and is sufficiently strong, you can start, for example, stacking droplets. And so this was kind of interesting work because it allows you, for the first time, to 3D print metals at room temperature. Now, not in any way that's structural. Truth be told, if you hit the table that this is on, it would fall over. Because it's only held together by a 3 nanometer layer, oxide layer. But this layer forms so fast, you can do a burst of pressure, and it will oxidize midair and sort of form its own hose. Like a garden hose, it's liquid on the inside, so you can drag it around, and it's electrically conductive like a metal. And this is about as close as we get to biology in my lab. This is a dead bug. I even had somebody come to me at a conference like, "You're the dead bug guy." I was like, "Oh man, that's not what I was going for." But anyway, a student did this as a joke. The bug was already dead. And anyway, he did this as a joke, but I really like it because it shows how small these structures are. They're about 100 microns in size, and it's truly a room temperature process. So this is one way you can pattern it. You can also pattern it by injection. Now, obviously, you couldn't do this with aluminum or copper, at least not in an easy way. So this is what we call a microfluidic channel. It's just a tube. There's an outlet hole right here. We use our thumb that breaks the oxide very easily, and the low viscosity allows it to flow in. Going to do it again from here to here. You'll see it flow through and pop up on the other side. So this is kind of an interesting way to pattern metals at room temperature just by injecting them. And we've used this to make different types of antennas. This is a coil for wireless power transmission. This is it's called a dipole antenna, like a bunny ear antennas you might have on your TV. And they're soft and stretchy. Turns out it's even easier to pattern. So let me go back for 1 second. This has an inlet and an outlet hole. So when you inject through the inlet, the air escapes through the outlet, obviously. And this, we actually have a single inlet, and over that we place the liquid metal. So imagine like an ice cream cone where you put the ice cream on top of the cone. And you can barely faintly see it, but these are microchannels, and there's no outlet hole. But we put this whole thing in a vacuum chamber, which you can't see, and we pull vacuum. Turns out that pulls the air out of these channels, so they're under vacuum. And if you watch carefully, you'll see the reflection of my student. He's going to come up, turn the valve, and that's going to let the air back into the channel. And when that does, you'll see it kind of flutter. So now atmospheric pressure is pushing right here, but these channels remain under vacuum. Wow, you're hard to impress. I almost fell over. Thank you. I almost fell over when I saw this. This is like, hands-free patterning, so it's very, very simple. You're just using delta P, change in pressure. All right, so at the end of the day, if you can get this into, say, a piece of rubber, you can make wires that are stretchy like a rubber band. And this breaks a traditional trade-off that you find with composites. With composites, you take something rubbery that can be stretched to a high value but not conductive at all, and you can make it more conductive by adding things like silver or carbon and that kind of thing, but at the expense of making it less stretchable. We're able to get something as stretchy as rubber and as conductive as a metal. So this is a little video. We had some hollow... That's okay. All right, you can hear it. Okay. So you can hear there's no degradation in sound quality as we stretch these wires to very, very large amounts of strain. So 700% strain is about eight times its original length. That's a lot. So you kind of get the best of both worlds. All right. So got a little bit of a story to tell. A few years ago, about 6 years ago, I was very, very lucky. I got to do a sabbatical at Microsoft, and there was a rumor that Bill Gates was going to come through the lab, and I really wanted to show him these stretchy wires, but we all know that Bill Gates is very powerful, and I was worried he was going to do this. So the materials that we use, these silicone materials, tend to tear very easily. They're very easy to work with, but they don't have the best mechanical properties. So that really got me thinking, like, how do we keep this from happening? And so this doesn't exactly solve the problem, but it's kind of interesting to share with you. This was work done by Meredith Barbie with a collaborator at Duke named Steve Craig. And basically what she did was take these molecules that are called spiropyrens. And I know not all of you are chemists, but these are ring-shaped molecules. And just like physically, if you were to grab a ring and pull on it, eventually it might break open like this. Well, when this ring breaks open and it's part of the polymer that you see here, it changes color. So this little line here is the liquid metal, and we're going to start stretching it. And right about now, I'm starting to get nervous that Bill Gates is going to break this thing. So I'm going to tell you, please don't stretch it any further. And right around that point, right before it breaks, those rings start opening and the material changes color. And then when we let it go back, those rings will close back up and it goes back to being transparent. So we're not the first people to think of these molecules, but we just implemented it to try to address this problem. So this idea of color change, this talk is a little bit meandering. I hope you can follow along. But anyway, this got me thinking about color. And, we use color all the time. Like right now you're looking at a screen where information is being conveyed using color. So that's what this is showing. Mother Nature uses this for camouflage and survival, that kind of thing. So I had this visiting student named Yang, and he brought with him these pigments. This is a pigment that starts out blue, so we just mix it in with the silicone, we inject liquid metal, and then we run current through it, and that causes Joule heating, and when this stuff gets warm, it changes color. So, okay, kind of obvious, but looks nice. And there's different pigments. This is a red pigment, and we pattern the liquid metal to make it look like the NC State logo, so that's kind of cool. And if you look at with a thermal camera, you can see indeed this is just a thermal effect. All right, so there's a little quiz. What happens when you mix red and blue together? Oh my gosh, you guys are like sugar coma. Purple. Okay, so we mix red and blue together. We get purple, and we run current through it enough to reach one temperature, and that makes the red disappear. And then you run more current through it, that makes the blue disappear. So there's kind of multiple states here. Okay, so this is, again, it all looks really cool, but I mean, honestly, there's nothing new in terms of the science. And this also doesn't really take advantage of the liquid metal. So where this started to get interesting was this idea that if you really push down on these circuits, you can actually change their geometry because of the liquid metal. So what you can't see is there's a serpentine of liquid metal in here. And we're not running enough electricity through here to cause a color change. However, when you squeeze it, you change the local resistance, and that changes the color. So sort of the same principle. If you take a wire of this stuff, just like a wire like this, if you start stretching it, you make the wire longer and also the diameter narrower, and therefore the resistance higher. So at rest, it's purple, but when we start stretching it, so it looks purple, we start stretching it, you make that liquid metal wire longer, and now you increase the resistance, and you can start changing where that color changes. And this is kind of nice because there's no chemistry involved, no fancy chemistry involved, and we can control the strain at which these colors change based on the geometry of the wire and the amount of current that we apply. Okay, but still this is not all that, I mean, it's cool, but it's not all that maybe compelling. So to me, this is where it starts getting interesting. So if you want to pick up an object, like most of you just picked up a cookie or an apple or something, right? The first thing you do, typically use your eyes, but you could also just close your eyes and feel around using your hands. And there's sensors in your hand that send a signal to the computer, your brain, and then through some magic, our brain knows exactly what to do, not to crush the apple or not to let it slip. It's really amazing that our bodies are able to do this. And if you were to try to mimic it, you might use, in like a robot, you might use a sensor, a computer, and a machine, like some kind of motor. But the problem is, or one problem is, that just in the human arm alone, I've been told that there's something like 1 million sensors. So this causes a lot of complexity. So this is from one of my favorite movies when I was a kid. This is C-3PO. Have you guys seen Star Wars? Whew. I was about to walk out. Okay, so this is the scene where C-3PO gets his arm ripped off, and you can see all these exposed wires. So there's probably, there's more elegant ways to do this, but the point is wiring up a bunch of sensors is complex. So could we maybe get rid of the computer altogether so we don't have to send signals back and forth? Maybe the material just knows when it touches us, it knows what to do and responds. Now, this is a little bit of a pipe dream, and we're not even anywhere close to being able to do this, but it turns out it's kind of interesting. An octopus has its neurons distributed in its arms. About 2/3 of them are distributed in its arms, whereas most vertebrates, in fact, I think all vertebrates, as I understand it, have almost all their neurons in a centralized place in your brain. And so this is quite interesting because it means each arm is kind of its own brain. And well, ever since I've learned this, I stopped eating octopus. So I'm sorry if this ruins it for you. Okay, so now that I've told you how amazing an octopus is, I will show you something very, very modest towards this direction. Okay, so what do? We made a slab of rubber and we put liquid metal in it, and the circuit is labeled A, B, and C. We then flip it over, and you can no longer see the metal because it's inside of this pigmented silicone, so it looks purple. And we hook up 2 wires to this, and there's not enough electricity to cause a color change, even though there's electricity flowing through it. But then when we squeeze A, we push on A, we redirect more electricity to region C. And so you'll see a color change. Then if we squish A and B, we get a different state, which is a white output. So basically, you're just redirecting energy depending on the way the material's touched, but it's kind of neat because you're redirecting it to a different place in the material. So this is very, very modest, but the idea is, number 1, it's soft. Number 2, there's no neurons here, there's no transistors here, and there's a little bit of a logic, 0, 0, 1 kind of thing. So you might be thinking, well, that's cute, but color change, that's not that useful. So we made another circuit, and it's just 2 liquid metal wires labeled A and B, and they're hooked up to a motor. So this is mechanical and electrical LED. And you can make a truth table. So if you don't touch A, you don't touch B, then both the LED and the motor are off. So they're labeled, they're red. And then I'll play the video so you can kind of see what happens. If you squish A, I think they both turn on. It's hard to see, but the LED is now on. If you squish A and B, the LED's on, the motor's off. So you can kind of play tricks on the way you redirect the energy and the way that you get voltage drops through your circuit based on the way the circuit is touched. So I keep showing this to people. I'm not sure if it's just cute or useful. I'm not sure. You can be the judge. But anyway, I think it's kind of interesting because, again, there's no transistors here, and it's just completely based on the way the materials touch. It responds in a certain way. All right, so I warned you this is going to be meandering. This is one more thing I wanted to show you. About a year ago, we worked on this review. And if you've ever worked on a review, it's a lot of work. So my student, Vina, who worked on this, deserves a lot of credit. And one of the consequences of this is we put together this little cover art. And what we were trying to show, this was an issue focused on soft robots. So literally trying to make a robot more like an octopus. And since our focus was on energy harvesting, we made this robot that's somehow underwater and looking at this octopus very longingly, kind of jealous, because the octopus swims around and doesn't need a solar cell or a plug or any source of electricity. It just eats stuff. And here this poor robot has to get its energy beamed in magically through this light. Okay, so we're not able to do this, but that's the idea. Okay, so what we're really motivated to do is, we're working on these soft devices. And could we convert mechanical energy into electricity? And in particular, we were thinking about the human body as a source of sort of wasted mechanical energy. So for example, every time you take a step, you compress your shoe and it's kind of just wasted as heat. So could you somehow collect that? So this is a question: how can we convert this mechanical energy into electricity? And these numbers are actually quite large, shockingly large. It's almost hard to believe. But keep in mind, these are instantaneous power. So if you're just sitting there right now, obviously your shoes are not doing anything. But this is every time you would take a step. But, could we collect this and maybe do something useful? So start with something kind of a simple premise. And I don't mean to insult anybody's intelligence, but this is just to kind of get you thinking. The idea is if you had in space a positive and negative charge, they're obviously attracted to each other. So it requires mechanical work to pull them apart, just like it requires work to pull magnets apart or something like that. And if you let them go, they will naturally go back together. And so that movement of a charge on its own will is a form of electricity, or it is electricity. So how do you do this? How do you grab a positive charge and a negative charge? Well, that's not so easy. But one way to do it is to use a capacitor. So this is a picture of a standard parallel plate capacitor with the negative charges and positive charges, and we either want to pull them apart like this or slide them. And if you were to change the geometry, you change the capacitance, and that will drive charge. It's mechanical work which drives charge through your capacitor. Now this all sounds good, but if you think about the equation for this is the change in capacitance that arises from doing this kind of deformation. Changing the area you generate this amount of charge movement. And in order for this to really work, you want D to be very small. But now you imagine the challenge, how am I going to make a capacitor and move it like this without the plates touching, or slide them like this without the plates touching? That's not so easy. And so there are people who have done variable area capacitors before, but it ultimately runs into this problem. How do you mechanically move things while having this little D thing being really small? And D is just the distance between those plates. So can we decrease D? Can we get rid of, the charges have to come from somewhere. Usually that's a battery. And then how do you mechanically do it? You don't necessarily want to be limited to a sliding motion because, well, if I want to put this in my shoe, I don't want to have to, mechanically figure out how to make that happen. So the way that we do this is, surprise, surprise, we use liquid metal. And here's a depiction of the metal. And when you put metals in electrolyte, it will spontaneously form what's called an electrical double layer. This is just ions from the water. It will assemble at the interface with the metal and form what resembles a capacitor, where the distance D is on the molecular length scale, angstrom length scale. And so because that's in the denominator, that means you get a huge capacitance, and therefore, in principle, you could harvest a lot of energy. We're not the first people to think of this. There's devices out there that are called electrochemical double layer capacitors or supercapacitors. And if you were to look inside of them, they typically have electrodes made of carbon, and they have this electrical double layer where they store charge, just like a capacitor. But they're not soft, and they don't harvest energy. They store energy, but they don't harvest it. So what we did, and shown here in this little cartoon, conceptually is if you take liquid metal and you put it in a hydrogel, which is just a source of water, it's like Jello or something is a hydrogel, right? It will naturally form an electrical double layer. And when you squish it, like is being shown here, you'll change the area of your capacitor, where the capacitor is just the area of this liquid metal. And when you do that, you pull charge from another capacitor because you disturb the electrical equilibrium. And when you let it go, those charges go back. So that's kind of the idea. And these are very easy to make. We take hydrogel solution. So this is just water with some monomer. When we shine light on it, it polymerizes and becomes a gel. And you see we've molded it. And then in that molded structure, you can inject the liquid metal just from a syringe. You put more solution to encapsulate it completely, shine light, polymerizes, and then you're done. And the cool thing about this is very soft, and you can stretch it, you can bend it, you can twist it, you can compress it. Any mode of mechanical deformation will change the area of that metal gel interface. So of course we've characterized it, and when you squish it, you change the area that causes charging, and then when you let it go, it discharges. And so I'm showing you kind of the highlights, but we went in and characterized the electrical double layer, did a circuit model, and showed that it behaves exactly as you would expect. And of course, hydrogel is basically water, so no surprise, it works underwater. So that's kind of interesting because you could put it, say, on the body, or maybe for like ocean energy harvesting or something like that. So this slide sort of summarizes the idea. We've got the liquid metal in this hydrogel. We can deform it. When we deform it, we change the area. That drives charge through a circuit. And this takes advantage of the fact that you can change the area in sort of any mechanical mode of motion, stretching, bending, whatever. It takes advantage of D being very small at the molecular length scale. And there's no battery because this is thermodynamically driven. The electric double layer will naturally form spontaneously. Okay. So I didn't forget about Bill Gates. So, it's kind of a sad story for me personally. So Bill Gates did come by the lab, but he came one day before he said he was going to come. And so I didn't get to meet him, but I got to meet Paul Allen. So that was nice, but he did get to see the liquid metal. So that was good. One of my students was there and showed him. But we still really have this problem. And now I've shown you gels, and gels actually have the same problem. If you've ever eaten Jello, it's very easy to chew it and bite it. It just crumbles right apart. So we want to make a material that's tough, but also still stretchable. And I know a lot of you have kind of mechanics background, so I don't mean to oversimplify this, but what we want is a material that looks like this red curve, if you imagine stress versus strain. So a rubber band is really soft and stretchy. You can stretch it to really large strains, but it doesn't require much force. something like a piece of glass or a piece of metal requires a lot of stress to elongate it, but it doesn't go to very large strains and then it breaks. And what we want is something that takes a lot of force and goes to a large strain because it's the area. This is basically distance, this is basically force. Force times distance is energy. So the integral under this area is the sort of a measure of the toughness. There's a lot of work in this area. I'm not going to go over the background, but these are some of the folks that inspired what I'm about to show you. So again, how do we make tough gels? There's a couple issues with gels. If anybody wear contacts, you probably know that these things tear very easily. Even if you don't wear contacts, I think this is kind of a well-known problem. And my wife wears contacts, and when she gets them, they're shipped to her in these little packets, and she has to open them, and they've got liquid water inside. And the reason they have water is because without it, the water would evaporate and the hydrogel would shrink. And it can shrink quite a bit. Hydrogels can absorb a lot of water. So these are kind of two of the issues with hydrogels. We'll have a really amazing postdoc who had this idea of taking the water, the hydro part, and replacing it with a different liquid that are called ionic liquids. So we call them ionogels. And an ionic liquid is literally salt that is a liquid. So this is table salt, like you put on your French fries, you might have at your kitchen table. And this is an ionic liquid, which is also salt, shown here. This is one example. There are tens of thousands of these ionic liquids. This is just one that we happen to use. And you can imagine that because they've got these bulky side chains, it's a little bit difficult for it to crystallize, so it has a low melting point. So I need to explain a little bit of nomenclature. So we use, in this work, we use very common materials. So there's two things. We use polyacrylamide. This is the structure of polyacrylamide, and this has been used in the past for contact lenses. So I'm going to avoid jargon and just call it the contact lens material, if that's okay with you. And then the other material is polyacrylic acid. Here's what it looks like, and it's in baby diapers. This is what absorbs the moisture in baby diapers. So I'm going to call this baby diaper and this contact lens. So I'm going to show you a cool video, and then I'll try to explain what you're looking at. So this is the material that the postdoc managed to make. Okay, so this is the contact lens material with the ionic liquid, and you see it's very brittle. In fact, and you also see it's white. That's important. We'll come back to that. This is the baby diaper material in ionogel. It's very soft and stretchy, but it's not very tough because it breaks easily. This is a copolymer, so we polymerize the two polymers together. Hydrogel, so there's water, and it's not very good. This is the exact same copolymer in the ionic liquid. So all we've done is change the liquid that's in this polymer, and it's very strong for a gel. This is like 60 or 70% liquid, and it's very, very strong. Okay, so how does this work? Well, I'm a little bit concerned that my analogy here is not going to work since you didn't know Terminator, but do you guys know Goldilocks? Oh, thank God. Okay. All right, your childhood were not completely deprived. All right, so here's Goldilocks. You remember she goes through the woods, she comes into this house and finds these 3 bowls of porridge. One's too hot, one's too cold, and one's just right. And in our case, we've got these gels. Over here is 100% the baby diaper material, ionogel. And here's the contact lens material. The contact lens material is the brittle one. That's too brittle. The baby diaper one's too stretchy. And if we're in the middle, that's the just right one. And you'll notice that I put the just right where it goes from being transparent to white. The fact that it looks white is a sign that there's phase separation going on, just like how milk looks white. You've got little globules of fat in milk that makes it look white. And here, what happens is the polymer doesn't exactly like the ionic liquid. So as you make it more like this polymer, at some point, those polymer chains they're like spaghetti noodles, are swimming around, and they will collapse on themselves and form little domains. So try to depict that here. This is the contact lens material, baby diaper material, and this is them copolymerized together. This row is water as a solvent, hydrogel, and you'll see that all of them are very well solvated, the polymer chains kind of swimming around. So if you look in the contact lens material, this is the one that looked white. So what I'm depicting here are those phase-separated domains that have separated themselves from the ionic liquid. So they've kind of collapsed on themselves. And if you look at the stress-strain behavior, that's this red data, and it's very brittle. So it's really hard to break, but then it doesn't go to large strains. If you look at the baby diaper material or any of these, they're all very well solvated with the solvent. And you see that they stretch to very, very far strains because those spaghetti noodle molecules can stretch out. They can be elongated without any issue, but they don't require much stress to break. But when we're at the just right one here in the middle, that's this blue data. So I know the videos are cool, but like this is pretty wild because this is like telling you 1 + 1 is 10 or 1 + 1 is 1,000, right? We're taking a material that's very, very stretchy, but not very strong, and a material that's very brittle. And when you put them together at just the right conditions, you get something that's very, very tough, which is the area underneath this plot. So why does this work? Well, this is kind of our best explanation so far. We think that these domains, these polymer domains between the phase-separated domains are rubbery. So that gives you the kind of stretchability, the elasticity. But these little domains that, it's hard to depict, but if you imagine the polymer collapsing like this on itself, they're hydrogen bonded. And so when you pull them, you're actually having to pull those hydrogen bonds apart so they break and reform, and that dissipates a lot of energy. Okay, so enough science. Let's go back to cool movies. All right, so this is the copolymer hydrogel. Remember, this is like the contact lens material. When we drop a ball on this, you see it just tears just like you would expect. But when we do it on the ionogel, you'll see that it just bounces right off. Very, very good at dissipating energy. And, kind of neat, they also can heal. So when you cut these two things and put them back together, those little domains that I described to you, when you heat them, they become solvated, and then when you cool it back down, they lock the interface together. So it requires heat, but you can get this to heal. Now, this is a little bit of an aside from this work, but you can imagine integrating liquid metal into this. And this is actually a different polymer, but this is also a self-healing polymer. So this is the liquid metal wire inside of one of these polymers. And so there's electricity running through there that lights up this LED. And if you cut this in half, you will break the circuit electrically. And you'll see that, of course, the light turns off, but you also break it mechanically. And the key idea, though, if you have to look, it's a little hard to see, but the liquid doesn't come gushing out. It forms that oxide so fast that it stays flush, just like when you cut your skin, you form a scab. And it's flush with the interface, so when you bring it back together, it heals electrically. And then the polymer goes back together. In this case, it's using hydrogen bonding to go back together. So you have to wait about 10 minutes, but you don't need to heat it. There's no light. You just wait. Those hydrogen bonds wiggle around, find themselves, and it regains its original modulus. So you can come pull on it. And it's pretty tough. All right, so the ionogel, one of the interesting things, and I think the reason that we were able to publish it where we did was because it's really easy to make. And that lends itself to 3D printing. So these 3D printers, they use projectors of light into a vat of resin, and that resin needs to be a photopolymer. In other words, using light to convert it into a polymer. And that's exactly what we do. So this is the ionogel precursor. You can see it's just low viscosity. You can fill it into, in this case, between two glass slides. And we shine light on it. That light causes the polymerization, and then you're done. That's it. So even if you're not a chemist, which I'm kind of a crude chemist at best, even I could do this. You just mix it together and shine light. And there's your tough material. So you can 3D print it. So that's nice. Oh, you might be wondering, why is it yellow? The reason it's yellow is because we intentionally added a dye, because if you don't add the dye, the light goes too far into your vat of resin. So you actually want it to only go to a very thin layer, because 3D printing just does one layer at a time. Okay. So at the end of the day, this is why another reason this work is exciting is these are called Ashby plots, which plot two different things people care about, in this case, like Young's modulus and fracture strength. And these are different classes of materials that people have made tough over the years. Still, the gold standard, believe it or not, is Mother Nature. So here's natural rubber and cartilage. Cartilage is the material between your knees. It kind of takes the wear and tear. And the gels that we made are as tough as cartilage. In fact, by these metrics, even a little bit better than rubber and cartilage. So, and it's super easy to make. Okay. Can I have 5 more minutes and tell you about Yoda? Okay. All right. So I don't know if you know this word, coda. I just mean to mean the end. So we're on the home stretch. So hang in there. So what do I mean by the force? Well, liquid metals have enormous surface tension. Tension is a form of force. And does anybody know the surface tension of water? And pretty high because it's a polar molecule. You guys know? First year grad students? Sorry, I didn't mean to make this a quiz. It's about 72, so keep that number in mind. Okay, so most of the liquids that you encounter in day-to-day life, whether it be oil's about 20 or 30, I don't remember exactly. Water's about 70. So typically liquids are between 20 to 70. Okay? Liquid metal is like 700. Okay? So that would be like walking around and you see most people are 5 feet or 6 feet tall, and then suddenly somebody's 50 feet tall, right? So this is 10 times bigger than most liquids you would ever encounter, and it's not even close. Now, in this video, you might be thinking, well, what about the oxide? Well, we are intentionally doing this in base. This is sodium hydroxide, which keeps the metal free of oxides. So if you shake it violently, you can break it into drops, but I'm actually surprised how slow this is. I have a vial in my office and I show people, and sometimes I really have trouble breaking it into droplets. So what does that mean? It means it really wants to be a sphere. Well, a few years ago, we had a really amazing student who kind of by luck, and this is a really good lesson, I think, to the grad students. Sometimes you just got to try things. And it's a long story, but I'll just show you the end result. He ended up putting one of these droplets and attaching an electrode to it and applying a voltage. It's a positive voltage, so it drives the surface to form oxide. Now, earlier, you remember I showed you the oxide allowed us to 3D print the metal to make like stacks of droplets, so it's kind of a solid shell. But because we're doing this in that sodium hydroxide solution, we're constantly dissolving it and depositing it, so it can actually flow. And that 50-foot giant, remember the really high surface tension? We can lower that tension to very low values and get it to flow. Now you might notice it looks like smoke coming off of this electrode. That's hydrogen bubbles. So we're oxidizing this metal and we're reducing water. So there's a circuit here. It's just the electrolyte is transparent. It's just sodium hydroxide and water. So what in the world? We just took the 50-foot giant and made it look like it was a little, like a little ant or something. Well, my first thought was that this is what's called electrocapillarity, and this is a phenomenon that's been known since the late 1800s. And the idea is that if you have a liquid like, say, mercury or something like that, and you put it in water, they really hate each other. Like in that vial I showed you where you shake it, really hate each other, so it's got a large surface tension. So if you look at the surface tension, do you remember what it was for water? 70? Okay, so 600, that's a huge number. So here we are, it hates its surroundings. And we can trick it, though, into liking the water by applying a voltage. And if we apply a positive or a negative voltage, it doesn't really matter because you get the opposite ion that comes to the interface, which is these red color things. And the equation that describes this is the surface tension, which is what we're plotting, is that at the point of zero charge, PZC, which is here, minus 1/2 CV squared. Some of you are electrical engineers. What is 1/2 CV squared? Energy for a capacitor, right? Yeah. So this makes a lot of sense. You're making a capacitor, electrical double layer, and you can lower the surface tension. Everything's happy. It should be symmetric because it's voltage. One little annoying thing is that this is not centered at zero. This is kind of just ignore it. It's a weird electrochemical thing. It has to do with the materials of construction. But anyway, when you look at this, you might think, like I did, like, oh, that's great. If I apply a big enough voltage, I can make the surface tension any value I want, including zero. But the problem is, and this is data from 1965, they stopped at this voltage because anything beyond that, these charges start to combine and you get electrochemical reactions. Bubbles form, right? So you might notice that this does lower it from 600 down to 500. That's actually a pretty big change, but this is also still a pretty big tension. So this is not what we're observing. In our case, when we apply a positive voltage, it will spread like a pancake, and negative voltage, it beads up, and in fact, you can see it looks like smoke. That's hydrogen bubbles coming off the surface. So what is happening? Well, we made our own measurement with a droplet. We stuck a wire in the bottom, but just enough so it wouldn't disturb the shape. And what we do is we look at the shape of the drop, and the shape represents the balance of two forces, gravity, which wants it to be flat, and surface tension, which wants it to be a sphere. So you might imagine as the tension lowers, it will change its cross-sectional shape. And from that, we can tease out the surface tension. So here's our experiment. Here's the droplet. There's a little electrode just poking through right there. And when we don't do anything, here's that surface tension, about 500. Remember, water 70. Okay, and so here we are. This is when we're doing nothing. Again, it looks like we're applying a voltage, but we're doing nothing. This is what's called the open circuit potential. So here we go. We'll start the experiment, and we apply a little bit of positive voltage, a little bit, like a fraction of a volt, and the droplet starts to squish, and it's completely reversible. And so we're getting huge changes in tension, and it's completely reversible. So you might notice that over here, it looks kind of like a parabola. Remember, that's what we expected from the theory from the late 1800s. And it should be a symmetric parabola, but something weird happens right here. And it turns out that where that weird behavior occurs, where I've drawn this dotted line, is exactly where the oxide starts to form. We know that because when we measure the current, here's zero current, we see a little bump. That means there's some reaction occurring on the surface. And so what that means is over here, the anomalous behavior is due to the oxide. And over here, this is classic behavior, kind of boring, but still cool. Okay, so why we're still trying to understand this. I can elaborate during the Q&A, but we think it's acting like a surfactant. Surfactant is a molecule like soap. So if you hopefully washed your hands today, the soap goes to the interface between the oil and the water and lowers the surface tension. In our case, we apply 1 volt and we apply our soap, which is the oxide. Negative 1 volt, it goes away and it beads up. It's easy to put soap into water, not so easy to get it to go away. Ours is completely reversible and we're getting huge changes in tension. So here's a plot of tension. Here's poor little water. Water's 70, so here's about 70. And if you'll humor me, this is really not quite appropriate, but I've plotted tension here, but remember when I asked you what the tension of water is? I got a lot of blank stares. So humor me here, instead of tension, I'm going to keep the numbers here the same, but call this mass, just so you can think about it conceptually. So water is like a dog. It's a 70-pound dog. It's kind of heavy. You can pick it up, it's kind of heavy. And when you put soap on it, it becomes a little 30-pound dog. They're still dogs, but right? And liquid metal is a polar bear, 600-pound polar bear. And when we apply 1 volt to it, we turn the polar bear into a feather. But unlike the soap, which we can do one way, but not so much the other way, we can completely do this on command. Huge changes. So, last thing I want to show you. If you look at this data, you should be very mad at me, because why did I let my student graduate without taking one more data point? That looks like it's going to go to 0. What happens if a liquid has 0 surface tension? Gravity is... right? Well, remember, we only can take data when we can look at the shape of the drop. So let me show you what happens when he tried to do this experiment. This is with Karen Daniels. We looked at a droplet. There's an electrode sticking underneath it in a little petri dish. So you're looking top down, and we apply the voltage, and it spreads. So gravity is into the board, to the screen. And not only does it spread, but that 50-foot tall giant is now acting like 0-foot tall giant, or baby. And you'll notice that occasionally these little things will break off, and when they do, whatever was on the surface goes away because it's in the sodium hydroxide, and it just beads back up because it's got high surface tension. So we're kind of taming the beast with about less than a volt. It's actually 0.8 volts. Okay. I think I should stop because I had one more video I wanted to show, but I think I'll just, one more is okay. So you know what happens when you turn on your faucet? It drips. Well, that's called Rayleigh instability. If you do the same trick with liquid metal, it will drip. But if you start applying the voltage, which you can see here, we lower the surface tension because of this oxidation, and it will come out as a hair. The diameter of this is 100 microns, the same as a human hair. So we're taking the liquid with the largest surface tension known to man, and we're making a little hair. So here we've got the tallest container we could find in my lab. My daughter refuses to cut her hair, so it's really long. It's like my daughter's hair. So it's this tall, but it's 100 microns in diameter. And one of the cool things is do you remember this from freshman physics? Yeah, so in our wire, we've got current going through our wire. If we put a magnet behind it, we can get a Lorentz force. And the Lorentz force on a liquid, there's no resistance to it, so it should move. So if you imagine, here's our magnet, which you can't see because it's behind the screen, so I'll make that go away. But here comes the drop, and the Lorentz force whips it around outwards, and then it experiences Lenz's law at the perimeter of the magnet, and that slows it down because the magnetic field diverges at the edge. So gravity is this way. So I challenge you tonight to go turn on your faucet, form a stream the size of a human hair, and then get it to form spirals in midair. And you can do multiple magnets. So here's a couple. So that's kind of cool. And this is my last video.
This is really cool. This week, scientists at North Carolina State University announced they discovered a way to move and manipulate liquid metal with electricity. And Arnold Schwarzenegger has already been sent back in time to stop it.
So that put an end to the liquid metal research. So thank you.